This video is for a computer security course at Metropolitan State University. I'm going to be talking about encryption algorithms and how plain text is actually computed into a ciphertext. I have to issue a disclaimer. This video is solely for educational purposes only, and I'm not liable for any damages that may be incurred by someone viewing this content. Also, any views expressed in this video should not be associated with Metropolitan State University, the ICS department there, or my professor. Okay, off to the PowerPoint. So an encryption algorithm uses a key and a plain text as input to generate a ciphertext through a mathematical process. For the programmatically minded people, I have here a function called cipher, two parameters, plain text and input, goes through some mathematical process and returns the ciphertext. There are two types of encryption algorithms: symmetric, otherwise known as private, and asymmetric, otherwise known as public. Symmetric is faster than asymmetric. There are also many more algorithms inside the symmetric crypto system. Asymmetric, I'm only aware of 3, and any other ones just seem like derivations of the other 3. Symmetric is used for transport, encrypting large files. You would not want to use asymmetric crypto system to encrypt large files to then be transported over a network. And symmetric could also use for encrypting data at rest, files or files on the hard drive or the entire hard drive itself. And asymmetric is also used for creating digital signatures in order to authenticate or non-repudiate. Symmetric is inconvenient for networking. You can imagine the explosion of keys that would happen, and this would be very difficult for a key management system. Whereas asymmetric is very convenient, where the public keys act like a public phone book or something in order to be able to encrypt something with the public key and therefore give it to someone with the private key, and only that person can decrypt. Symmetric uses one single key, and asymmetric uses, as I mentioned, private-public key pair for encrypt-decrypt, and this operation is and vice versa. Symmetric operations on the data are usually performed in rounds. It's either a block cipher or a stream cipher. Stream cipher would not be rounds, but block cipher there would be rounds where each iteration produces an intermediate state. And asymmetric is based on something called a trapdoor function, where it is very easy to compute, but not so easy to reverse. Two different types of symmetric encryption are block ciphers and stream ciphers. Block ciphers transform text one block at a time, usually 128 bits, and stream ciphers transform 1 bit or byte at a time. The transformation in a block cipher is done in rounds or iterations, where the round process is unvarying and it ends in intermediate states. So when you hear of people breaking a block cipher, they are usually breaking it in rounds, solving for the intermediate states. And each round has its own round key that is generated from a process known as key expansion, derived from the original cipher key. A stream cipher uses a pseudo-random number generator to create a key stream by which the plain text is exclusively ORed with. And the original key usually acts as a seed for this pseudo-random number generator. One requirement of the PRNG is that it has to be cryptographically secure, meaning that the number cannot be predicted from the seed. Because if it is, then every single number after that would be predictable and easy to use for the decryption process. Confusion is the property of a ciphertext having no surviving relations from its key or plain text. This basically means that no patterns or repetition survives the transformation process. This is a bit difficult to obtain in a block cipher, hence the round and the round keys, which are different. Stream ciphers, confusion is guaranteed. Obviously, it's completely random. Diffusion is guaranteed in a good cipher. For a block cipher, diffusion is the property that if you change you change an A to a B or 1 to a 2, and then this propagates throughout the entire ciphertext, that it changes the ciphertext dramatically. Diffusion is not used since the text is changed byte by byte and it's already completely random. But this also ends up being a disadvantage in a stream cipher you can't really ensure the integrity of a message. If the ciphertext was changed in one little area, it might not change the plain text that drastically, whereas it would just look like a typo, or maybe it would look like a typo that would cause something to be significant. You know, $100 would turn into $1 million maybe. Whereas in a block cipher, if an attacker changed the ciphertext in one little area, you could tell that somebody messed with the text because the resulting decrypted plain text would look ridiculous. Encrypting and decrypting in a block cipher is very arduous, whereas in a stream cipher it's very easy. It's just an exclusive OR function, assuming you know the key stream or the key to put inside the pseudo-random number generator. So I have here the announcement of the Randall algorithm as the Advanced Encryption Standard. This is Federal Information Processing Standards Publication 197. I just wanted to show you a little bit how the algorithm is actually done, how the text is actually ciphered. So bytes are represented as polynomials. So if you see a polynomial, don't be confused. I guess it's just a byte. So this would be right here. This byte would be represented as this polynomial. It does make it easier to see what's going on, or it can be represented as in hexadecimal format. So here, 4x4 array. You have your 1 byte inside each of these little blocks, and basically you have transposition, substitution types of ciphers being done on them, multiplication, addition. It then goes on to describe addition. Addition is just exclusive OR operation. Multiplication, if you multiply 2 bytes, you can end up with a very large polynomial, which is not desirable. Well, then you just take it modulo this irreducible 8th degree polynomial, and you get a new byte. Polynomials with coefficients, this is when you represent an entire row. So this a sub 3 coefficient would just be the byte inside that block, and here you'd have 4 blocks that would represent basically this entire can't highlight it, this row. Inside this specification there's also the cipher. So here you see the pseudocode for the cipher. And I mentioned rounds. Here's the round. You have all these different functions being performed on it, and you have a different round key for each round. The key expansion mechanism is also described, in which you end up with the key schedule. From one original key, you end up with 44 round keys. Why 44 and not 40? Because there's 10 rounds in 128-bit with a 128-bit key. I'm not entirely sure. I'd have to really look at this in more depth. But then there's the inverse cipher. You have here rounds, and you have the functions as invert shift rows, invert subbytes, add a round key, invert mixed columns. So that is the general idea of a block cipher symmetric encryption algorithm. If you want to take a look at it, I will include the link, and you can see actual examples of it at the end of the paper. Asymmetric encryption was first invented by scientists in the UK's Government Communications Headquarters. James Ellis came up with the concept, and Clifford Cox came up with what we now know as the RSA algorithm. Also, the Diffie-Hellman exchange was also invented by scientists in the GCHQ. I think it was another man, but I don't remember his name. The work was kept classified until 1997. I had here an interview with Clifford Cox that I found interesting, but I don't want to extend this video past the 15 minutes. It was independently invented by Whitfield Diffie and Martin Hellman. That's the Diffie-Hellman exchange. They also gave credit to Ralph Merkle. He came up with the concept. This was the key exchange protocol based on the discrete logarithm problem. I'll get into that in the next slide. Ronald Rivest, Adi Shamir, and Leonard Edelman published the most widely used form of asymmetric encryption today in 1977, otherwise known as the RSA, and the trapdoor function there is based on prime factorization. In the Diffie-Hellman key exchange protocol, the symmetric key is jointly derived, not exchanged. So for users I and J communicating over a network, their public keys, which are found taking some number A raised to the public or the private keys as the power here x mod q, and the other one does the same for their private key to derive their public keys. Their public keys are shared over an insecure channel. Their private keys are kept secret and then used afterwards to combine with the other public key to generate their symmetric key, their shared common secret. So here, if the symmetric key is represented as capital K here, sub ij, it would equal one of the public keys raised to the private key of that user, mod q. Any eavesdropper would know the public keys, but not the private key of either user, nor would he be able to generate or derive those private keys from the knowledge of the public keys. And also calculating the symmetric key from both public keys is computationally infeasible. This is known as the discrete logarithm problem. However, there are weaknesses in the way that Diffie-Hellman exchange is implemented over the web. There was a conference paper published in 2015 showing weaknesses through a massive collection of pre-computations of the same primes. They were able to show that the discrete logs could be solved as long as the primes were known ahead of time, and some of these primes being 512 bits rather than 1024. Remember, the prime is the mod q. That would be the q in the equation. They did this through a logjam attack in which a man in the middle forces the server to downgrade into an export grade crypto, be using 512-bit. Basically, that just, from my understanding, means retrograde. The word export just comes from some U.S. regulation dealing with that. There was a correlation between leaked NSA documents from Snowden in 2013 and the results of this paper. Namely, could have been how the NSA was decrypting VPN and TLS traffic. But there has since been a rebuttal of this paper, and I have here the link of that critical review. They questioned the estimations and the methodology used in this other paper. They questioned the practicality of it, but they did not really, from my understanding, question the actual computation part, meaning that it can be done. It's just how widespread can it, how much of an effect does this really have? So in the RSA encryption algorithm, keys are actually exchanged, not derived like the previous one. It is based on the difficulty of prime factorization of very large numbers, hence the 2048 or 4096-bit keys. In the algorithm, the first step is to choose two very large primes, p and q, and multiply them together to get n. You calculate phi of n, which is the number of numbers less than n that are coprime with n. It turns out that phi of n equals p minus 1 times q minus 1, because p and q are prime, which means that no other numbers below it are going to be share any common factors, and phi of n is multiplicative. You choose e to be greater than 1 but less than phi of n, and coprime with n and phi of n. E is a number that makes up the public key along with n. The private key is then generated from this information, the private key being d. This equation right here, d times e mod phi of n equaling 1. That is, so d would be the modular multiplicative inverse of e. So you can see that without knowing the prime factorization of n, calculating phi of n is infeasible, and then therefore getting the private key from the public key is also not very difficult to do. So in taking a look at how this would actually work, after having calculated your E and your D, your public and your private keys to encrypt something, call it M, the message M, we raise it to the public key, mod n, and we get our ciphertext. To unlock it then, the recipient would then take this ciphertext, raise it to the private key, who only they have. Someone else is encrypting it with their public key, and you do an operation mod n on it, and you would get back the message. I do need to clarify that in multiplying C by itself, E number of times or D number of times, that you are wrapping this number around n, so that n is the finite field, and that's where the mod n comes from. The last form of asymmetric cryptography is elliptic curve cryptography. It's by far the coolest in my opinion. The equation up there for the curve, y squared equals x cubed plus ax plus b. Because y is squared, it has horizontal symmetry across the x-axis, and this is used in generating the points. The general idea is to specify a base point, call it p, on the curve, and you have some function, let's call it add, and you add that point to itself a number of times, which is your private key, the amount of times that you add it to itself, to arrive somewhere else on the curve, and that is your public key, the point that you end up on. The addition operation is like drawing a straight line between 2 points and then dropping below the x-axis from the third intersection point on the curve. Once you drop below the x-axis, if you are above it to begin with, or you rise above it if you're below it to begin with, that comes up with your next point that you then add p to again. To start with, you add p to itself, and this is a tangent line. The picture on the right illustrates what p plus q looks like. You end up with the point r. Of course, if you could imagine r being the point below the x-axis, though not above it, because you would then drop down below it. And then to add p plus r, you can see that the intersection point would be somewhere in the middle of those 2 points, and then you would rise above the x-axis to its corresponding positive y value on that curve. And this is used much like the Diffie-Hellman key exchange protocol. The private keys are kept secret, the public keys are shared, and then once the public key arrives at the other side, you use that point to then add p to itself again, the your private key's number of times, to arrive at a shared common symmetric key for that session. In reality, the curve looks more like something on the right here. This is a bunch of plotted points of an elliptic curve that is wrapped around a finite field. That's where the mod p, that's the effect of mod p. Just similar to the way mod p was used in the other asymmetric crypto systems. You're just dealing with a finite field. And you can see that a 256-bit key provides as much security as a 3072-bit key for RSA or Diffie-Hellman. It also is much faster in creating digital signatures. So you may be wondering why elliptic curve cryptography is not used more than RSA on the web. And the answer lies in people's distrust of the NSA and the standardization process. Basically, the NSA's dual elliptic curve pseudorandom number generator uses 2 elliptic curves to generate pseudorandom numbers. And many lead cryptographers suspected of having a backdoor in it for many reasons, one of which it's 1,000 times slower than other PRNGs, yet NIST still standardized it. The NSA pushed it. There were some news articles that were suspicious, and then came the Snowden docs suggesting that there was indeed a backdoor. And if this is true, then elliptic curves can be manipulated to create a backdoor inside them that would sacrifice their security. Many patents exist also for some of these curves, and people want to avoid the legal issues of that. And also, interestingly, in 2015, NSA had a policy statement urging people to move away from elliptic curve cryptography and to focus instead on quantum computing for solutions in cryptography. And I have here a link of an article written by Neil Koblitz and Alfred Menezes. I hope I didn't butcher those names too bad, but those are a couple of cryptographers and the papers about their evaluation of this move by the NSA in this policy statement to move people away from ECC and towards quantum computing. In this video, I'm going to demonstrate how to encrypt a file using ActScript. I chose ActScript because it's really easy to use, and it's different than GPG, which is what we used in the lab. I didn't want to just repeat the lab exercise. And also it has, the servers are in Sweden, and it gives you an idea of how the public keys are used in order to share files with other people who have IDs on that server. So to encrypt is very easy. There's 2 ways that I can do it. I can hit this plus sign here. I can just go and select my file that I want to encrypt, which is a Word doc called demo. And then notice here that it's encrypted, and the icon has changed from a Word doc to an ActScript icon. I can decrypt that and stop securing it by just right-clicking on the application and say stop securing, and there it changes back to a Word doc. I can also encrypt from the File Explorer window itself by just right-clicking the file, going to ActScript, and then hitting encrypt. And here it asks me to provide a password, or it doesn't ask me to provide a password because I'm already logged into the ActScript application. Otherwise it would have asked me to supply a password. And the same thing goes if I were trying to open a file that was encrypted, it would ask me to provide a password. Another feature of ActScript is the file sharing that you can do with this. So if I were to click on this little people icon here, I select a file that's encrypted that I want to share, let's say this one. I can then provide someone's email address saying that I want to share this with them. I don't have anyone to share it with, really. I don't know anyone else with ActScript. And this is also only available in the paid-for version. It's like $36 a year. So maybe that's not for you. I probably don't have any use for it either, so I'm not going to pay for that. But anyways, that's how you would do it. How it's done is you have a public-private RSA key that's kept on the server based in Sweden, and the public key is used to encrypt the symmetric key that is used to encrypt your file, and their public key is also used to do this, so that when you share this with them, they get an email with the file as an attachment. They open it up, and they just have to use their password to open up this file, which would then use their private key to decrypt the symmetric key that was used to encrypt the file. Then they use that symmetric key to decrypt the file. Another feature of this, you have to pay for it again, of course, it was password management. I haven't looked into it all that much, but that's useful as well. But the free version for me is good enough. I can encrypt files locally. I can put them on a hard drive. I can put them on Google Drive or OneDrive, and they can be encrypted and they can stay safe there. So one last thing, I wanted to show you what my public key looks like. Here you see it's an RSA key. It's 4096 bits long. So this is either the product of two primes, or it's the product of two primes plus E. Remember, one of the modular multiplicative inverses, one or the other. Alright, so that's it for my individual video. Goodbye. Okay, so never mind, not goodbye. I have to properly conclude this video. So let me just say that if I have said anything that was inaccurate, I wouldn't be surprised, so please let me know. You can do that via D2L or YouTube or in person. Just let me know. I would like to be corrected if I've said anything wrong. And also, I hope you've learned something about encryption algorithms, the math behind them, because I certainly did. And in learning about it, I feel less secure. How about you?